Hello. I want to present to you TrenchBoot, which is Open DRTM implementation, and not only for AMD platforms, but I will focus on AMD since we're doing this part of job. So my name is Piotr Król. I'm founder and embedded system consultant at 3M, a Poland-based consulting company. I'm interested in open source firmware, platform security, trusted computing. So just one small note: all the presentation made by 3M had associated paper. So if you really want to know more about that, you can read exhausting paper, which will be published after this presentation. Okay, what we will talk about is a little bit of terminology, but I see that most of you are familiar with trusted computing and DRTM stuff. But we will repeat some terminology. We will see what's the difference between static root of trust and dynamic root of trust, and maybe a little bit about this holy war, because definitely there are two camps, despite those solutions are orthogonal, to be honest. Then I would like to show you some diagram from Trusted Computing Group specification, just to put the ground what we're talking about and how this flow work. I will switch to our implementation, a couple problems that we had, and then I will present demo on our CoreBoot platform, PCNG's CoreBoot platform that we maintain for a long time. And then some issues and what we plan to do further with that work. So what was the motivation? So we want to implement TrenchBoot. TrenchBoot is a open toolbox, you can say, because this is not exactly framework. There are many components to that. For AMD platforms, there were a couple of questions about platform that we maintain. So definitely it supports DRTM, but there was no software stack that can leverage that, or the software stack existing were not usable exactly in correct case. So yeah, so it would be great to provide out-of-the-box support for DRTM in all components, like in bootloader, in Linux kernel, and this is what we try to do here, and we succeed. And of course, we want to raise our knowledge about trusted computing and build better hardware, more secure hardware, and firmware, of course. Okay, a little bit of terminology. So what is root of trust? So root of trust is a component performing security-specific functions. This component can be ME, can be, if you trust it, can be PSP, can be OpenBMC. I saw discussion that what if BMC would be a root of trust. This is some component on our platform typically. So a root of trust meant for measurement makes the initial integrity measurement of the executed code and put it in something tamper resistant, which can be which is trusted platform module, so TPM. And so there are other terms here, like core root of trust for measurement and static root of trust for measurement. So Michał explained that yesterday during the presentation. But in general, core or code right now, since Trusted Computing Group changed the glossary from core to code, not sure why. So code root of trust for measurement is the instruction, or are the instructions executed by the platform when it acts as a root of trust for measurement. And static root of trust for measurement provide chains of measurement. So we have these stages of booting, and each stage is measured, and the measurement is in TPM. And what's the difference between the dynamic root of trust for measurement? So dynamic root of trust for measurement is some platform-dependent function, which can be, typically it is instruction on Intel, and on AMD it's different. So on AMD we have SKInit, on Intel we need Intel TXT, and there is instruction sentry, and there are a couple of leaf functions. that help run the DRTM. And what this instruction does, it provides a new instance of root of trust for measurement without rebooting. So to establish static root of trust, we have to boot platform since it begins from the boot, and then at some point we have measurements which we can check. And in case of DRTM, we don't really care about those early phases because we dynamically establish this root of trust. Yeah, so it establishes minimal trusted computing base, which is kind of code which is self-defending. This is self-defending code, and I will show you how it happened. But what's the difference between static root of trust for measurement and dynamic root of trust for measurement? So first of all, I mentioned that we need reset for static root of trust. Second, there is problem with the PCRs since when we have update, we have to somehow reevaluate that, maybe reprovision TPM if we have some secrets sealed to PCRs. So it's kind of problematic, and to be honest, I don't know about anyone who implement that correctly in open way and deliver this widely. Other things are that various specifications are closed, and there are no open tools for a kind of provisioning platform with static root of trust. So of course in core boot we have vboot, but if we're talking about the hardware specific mechanism like NXP hardware assured boot or Intel secure boot or boot guard or AMD hardware validated boot, it is tied to closed tools which are typically available under NDA, and there are a lot of problems with them. So static root of trust is well established with major independent BIOS vendors. So typically you have platforms, UEFI platforms that are shipped and support secure boot is supported. There are open implementations, as I mentioned. There is vboot and Chromebook and PC engines use the open implementation. So dynamic root of trust for measurement in theory works even in compromised environment. So we don't really care about what happens before we did this instruction that establishes dynamic root of trust. So we don't have to reboot to establish that. We don't have like typically DRTM should be associated with remote attestation. So to be honest, some remote server should say to us if the measurements are correct or incorrect. And it is very small, like the secure loader, which is used during the execution in case of AMD is 64K. So it is possible to get through some certification. And with TrenchBoot, we have open implementation for that. So why to not use that? So this is picture from TCG DRTM architecture specification. So what we see here is platform boot flow. On the left side, we have platform power on. Then we're getting through pre-gap stage. So in case of Intel TXT, this is needed because it uses some closed binary from Intel ACM BIOS to pre-configure environment for further dynamic launch event. This for AMD, this is not needed. Then we either have SRTM or we don't have SRTM. So we boot our firmware. DCE preamble is kind of preparation, configuration, like environment configuration or preparation of the environment to run dynamic launch event. Some steps are needed typically. So we have this dynamic launch event. This is exactly our SK init or sentry instruction. And then we have some code which is run. In case of Intel, we have ACM, which you can download from Intel website. In case of AMD, there was nothing available just out of the box. So AMD does not provide anything, but there were various commercial implementation. And with TrenchBoot, we have open implementation of DCE. And then either we have success and we have a dynamically launched measured environment. So we run some kernel or some other software, and we can check PCRs that everything was dynamically measured, and we can check those measurements. Or we have some remediation if this didn't succeed. Okay, so this dynamic launch event use PCR 17 to 22. Those are initialized with -1. And during the event, the execution of the instruction, it is changed to 0 and immediately extend with the hash of our DCE, which can be either ACM BIOS plus probably something else. I'm not sure. I don't understand exactly steps for Intel TXT, but for AMD, we have our secure loader, which is measured, and it extends the PCR 17, which I will show you later. So I told you a little bit about the implementation. So yeah, most of that I already told you. So the problem with Intel TXT, from my point of view, it is that it uses closed binary ACM BIOS. So up till now, I heard some rumors that there will be implementation in coreboot. I know that some people in 9-elements working on that, but still they will not open ACM BIOS because it's impossible. Intel will not allow that. So that's kind of key problem with that implementation, in my opinion. And then we have AMD, which is very well described in software manual. You can implement a completely open source version of the ACM for AMD. So it's called differently. It's called secure loader. But anyway, so there are some rumors that Qualcomm will have something soon. It was mentioned on Zen Summit. And you know, both all the implementations will be probably compatible with TCG specification. But the problem is that each of this dynamic root of trust measurement implementation use different terminology, and it's like when you're reading that, it's complete mess, and it's hard to new beginners to understand what's going on. So this is comparison of the terminology used by various implementation. So TrenchBoot typically tries to use TCG terminology, but there are some things that are not named, or we taking shortcuts. So the gap, you saw the gap is the stage where SRTM is running, and we really don't care what exactly going there because this is non-trusted environment. Then we have this dynamic launch event, which is SKInit instruction in case of TrenchBoot. In case of AMD, I'm sorry. In case of TrenchBoot, it is called as vendor call it. Yeah. So DMA protection from TCG specification is in AMD feature called device exclusion vector, which gives us ability to protect against DMA attacks in specific way. So I will not read that. Like you see, what's the difference between various implementation. Probably ARM has its own terminology. They also has some specification related to DRTM. Yeah, so as we are part of the TrenchBoot community, so we're also trying to clean it up. And hopefully, after some time, we will have common language to talk about that. Okay, so in case of problems we had, so typically we want to protect ourselves against two issues. So those are mentioned in trusted computing specification. This is DMA and SMM. So we have to ensure that code cannot be changed by anything outside of our trusted computing base, so from our small piece of code. But various things may happen. So typically we have something like we start our DCE, we measure, we extend PCRs and execute component, and we follow that with all the components. But it may happen some corner case situation where we measured and extend the component, but when we try to execute something like DMA or SMM, caused that that there was execution of some roach component. And to be honest, despite we have correct measurement and correct extension of the PCRs, we're running some roach component because of the manipulation through DMA or SMM. And in that way, of course, DRTM will not work, and this causes problems. Because of that, we have to protect ourselves about DMA attacks. So who understands DMA attacks? Who knows how it works? Like probably everyone. So it's like I mentioned that last year on presentation. So I will not repeat myself. There are in general two general groups of mechanisms to protect yourselves against DMA attacks. It's exclusion and translation. So VTD typically implements exclusion. It uses something called DMA protected ranges and protected memory regions. Of course, like you have to read VTD to understand how to configure that. AMD uses device exclusion vector, which in our opinion, is a little bit better since we have continuous array of bits and we can slice it, slice memory in 4 kilobytes and say what kind of protection we have. So this 4 kilobytes is not the random number. I believe it's because of the PCI config space. So like I believe this is related with PCI. And the translation mechanism is used when we have IOMMU or VTD DMA remapping. It's more complicated. You have to configure IOMMU correctly. You have to take care of specifics of the IOMMU hardware. And typically DRTM use exclusion, at least in the implementation that we saw so far. SMM. So this is quote from DRTM specification. So you can see that the DCE, so dynamic configured environment, shall consider SMM to be correct by construction, whatever that means. The SMM implementation shall successfully maintain its code and data integrity indefinitely. So yeah, so the assumption is that when we're getting some SMM code, it's correctly developed and correctly shipped by BIOS vendor. And to be honest, we have very little to protect ourselves. I believe Eugene STM can help us with that. But the question is how we can connect that with the DRTM implementation and what, how many resources we will need to connect those two things. So SMM, in our opinion, is one of the most problematic areas. So IBVs should ensure that all the handlers are safe and correctly implemented. But like we saw that we cannot rely on that. There were problems already with SMM. So typically, after setting everything up, we're locking SMM. There is no way to validate SMM code after this locking. So despite if we have open source firmware, we can investigate and we can check those SMM. And even if we use SRTM, we can even measure that. And in DRTM, we can even verify those measurements if those are fine. But still, we have situation that ring 0 can change SMRAM, and we of course have correct measurement. But after that, someone changed what we're executing, so this doesn't help. Yeah. So as I said, like the only option is SMI transfer monitor. But the question is how to implement that for AMD. I believe right now it's completely out of scope. The AMD programmer's manual is saying something about that, how there are some guides how to implement that, but still this have to be considered. And we have to think how to do that. So I just mentioned a couple implementation of DRTM that were even commercially successful. So first of all, first Oslo was just the research stuff. Flickr and Softcard were part of the commercial products, but they didn't go into the open, so everyone can use that. So because of that, TrenchBoot was created to provide open implementation for DRTM. Also, there was a GE implementation that they tried to integrate with TBoot. TBoot is a software that uses Intel TXT, and of course, this was out of the agenda because this is AMD, and TBoot didn't consider to merging any AMD code. Okay, so our implementation. So our implementation, if we compare that to the picture from TCG specification, looks like that. So we have platform reset, then we have core boot, then we have grab as a payload. Everything is, all that stuff is in SPI. Then we have in grab, we have slaunch module. This is extension to grab. And we invoke skinit instruction. We have this secure loader, which is called landing zone in TrenchBoot, and it can run Linux kernel, measured Linux kernel, what I will present you in a second. So how it looks, this is piece of code from grab config. So we typically have some path to Linux kernel, and then we claiming that we want to use skinit. There is alternative also for Intel version, like people from Oracle developing Intel version, and Apparatus Consulting. And then we have slaunch. This is our secure loader, which we take from the SPI flash. This is indicated by this CBFS disk. And then we boot. The difference is that the boot command is not exactly boot command that we typically run in grab. It is modified because we run those two previous things like slaunch skinit and slaunch module. It changed the memory layout in a way that when we booting, we executing skinit and running a landing zone, not the kernel, because in normal case the boot will cause jump to the kernel and we just put limits. And in that case, we want a little bit different flow. Okay, let's show a little demo. So I have my PC Engines board. There is a TPM module here. To be honest, the disk is not needed. Everything is in SPI flash. So let's boot. Yeah, so just to show that the config contain things that I told you. So there are some debugging stuff here, but we have so CBFS means that this is in SPI. So we're loading this kernel with those parameters. We have some init.rd also here to be able to have some user space, and we just executing slaunch skinit, slaunch module, CBFX, LZ header. So this is landing zone. This is TrenchBoot. To be honest, of course, this was already executed, so I don't have to kind of source that file second time when I just boot. And I can and you can see that the PCR 17 and PCR 18 was extended. I would like you to remember that value, the PCR 18. The PCR, like maybe not whole, like at least a couple signs. If you can whole, like I have no problem with that. So you should get a beer if you can remember whole. So 13 AD, let's say, the 17 contain our landing zone measurement, and 18 contain command line. So if we change command line, we should be able to modify the PCR 18. So let's say our attacker changed the command line to get some advantage. So I have to type that. And let's say I will leave the early print k. I will not add this early print k. And I need enter d to be loaded again. Since the memory layout is the same, like nothing changed, I will not rerun the slaunch skinit and plus slaunch module, since everything should be set up. I'm just booting. Okay. Yeah, so you can see that the PCR 18 changed since we have 13 AD here. So that means that change in command line caused change in measurement, what means that our secure loader really do the measurement. Of course, it's very hard to prove that we really run skinit. You just have to trust me or read the code. So I don't know how in other way I can provide that information. There is this log like invoke skinit. It is from the grab module, and then we have some logs from inside the landing zone or our secure loader, which are just debugging information that we extending PCRs and so on. Okay, so that's it from the demo. Okay, so what we plan to do with that? So you saw that I just show you the SHA-1 PCRs. So we want to also have a code that do SHA-256. But like for now we just don't have that code, and using TPM for that would have be a little bit problematic and slow, since we have to slice everything in 1 kilobytes and feed the TPM with that. This would be slow operation. And for now, we're not doing that. So either SHA-256 have to be implemented somehow in secure loader, or I don't know, like, or we have to live with SHA-1, which is not cool. The SMM and SMI problem have to be addressed. Like this implementation is better than what we have before, because before there was nothing. So right now we have like some remaining small problems with SMI. And yeah, so it's right now the only reasonable mitigation probably would be to use SRTM and just measure everything and make sure that the firmware didn't change. So this is the way we can check that SMIs were not modified. We're not measuring ACPI tables, and we should. And DRTM specifications say clearly that that we should do that. There is even special DRTM resource table which should be created. There should be consideration about supporting different OS and hypervisors. I hope to have presentation on Platform Security Summit 2019. Where we will show Zen running, but I don't know if this will succeed. I have not too much time for that. There is also idea to have iPXE and CBIOS working with DRTM. iPXE would be very cool, I would say, since in that way, for example, we can attest if things booted from server are correct. Yeah, and there is of course need for building custom kernel and custom rootfs, and it would be great if you can use Yocto to build like a small kernel and rootfs that can support various tools for embedded applications and use, of course, DRTM. So where to go from here? We're working on putting all patches into the TrenchBoot GitHub account. There is Google Groups, TrenchBoot Devel. I'm not sure if this is like probably clicking join and then Daniel Smith see some notification about that, then he can approve. Yeah, you can try this code. Like the main thing right now is trying that on different AMD platform that we did. We use quite old one. So yeah, so this is Puma SoC. So it would be great to check if there will be any problems to use that code for newer AMD platforms. And yeah, and we are open for discussion. And if you have any comments, questions, feel free to ask. Everything is clear. Obvious stuff. I don't know why we didn't completed that before, sooner.
There was one thing that bothers me in the future improvements. You have stated a support for CBIOS.
Yeah.
Could you explain shortly how would you implement that? How to see that?
Yeah. So the CBIOS would be like grep in our case. So it's like how I will implement that. So this is not. So CBIOS can read from CBFS, so it can get secure loader, and it can get other kernel and other things, and then it can invoke some assembly to invoke SKInit to jump to this dynamically launch measured environment. So it will be cool if CBIOS also supports that, not only grep. I think that would be the way. Okay.
All right, then. Thank you very much.
Thank you.